In this video, we're going to cover the distribution of the sample mean, or what I sometimes like to just call as a sampling distribution. And before we do that, we should review a little bit of notation here. So let me go ahead and highlight some things. So, right, we use mu when we're talking about the population mean, and we use x bar when we are referring to the sample mean. Okay. That's one thing. All right. Now let's talk a little bit about this so-called sampling distribution. Okay. So this is the sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. So for us, that word statistic for now is going to be replaced with an X bar. We're going to do this also later with proportions. That'll be our other statistic, will be the sample proportion. But so when we say that we're looking at the sampling distribution right now, we're going to be looking at the sampling distribution of sample means. And these sampling distributions, they are specific to a certain size of sample. Okay. And so we're going to start constructing one here in a minute. But do note that it says that it's a sampling distribution is really going to be the distribution of all possible sample means is really what we're going to be looking at. Or all possible samples. Maybe I should word it like that. So I'm going to have us come over here to look at a little program here. And so is what we have going on here. I'm going to make this a little bit bigger. In the green there at the very bottom, it's kind of hard to see because the histogram bar is so tall here. But that is a population that has a mean of 100 and a standard deviation of 15. And to be more specific, this is how IQs are distributed. And so is what I've done is this is how I want you to think about it for a moment is I've sent out one student, right? It says one sample. I sent out one student to survey 25 people and then average their IQs. Okay. So they reported back to us a mean IQ for that sample somewhere between 99 and 100. Okay. And so this one happened to land pretty close to 100. Okay. But I want to make it evident that this isn't what always happens, right? We could have drawn a sample of 25 and not ended up in between 99 and 100. Let me try and run it one more time and see if we get a slightly different result here because it's supposed to be random. And yeah, you can see we landed a little bit further from 100 this time, which is the mean, okay. Which is not that unexpected, right? Samples are not always going to have the same mean as the population, okay. But on average, they will, okay, which is what we're going to see. So I'm going to bump this up a little more and try to explain it again. I'm going to have us actually, we'll go to 5. So this time, it's as if I sent out 5 students and I had them all survey 25 people, okay, and then report back to me the mean IQ for their samples. Okay. And so you can see we ended up with one sample that had a mean IQ somewhere between 90 and 91. Another one which had a mean somewhere between 96 and 97 for their IQ. Then it looks like we had 2 students report back mean IQs between 101 and 102. And then for one more student reported back a sample that had a mean between 102 and 103. All right. But I'm going to start bumping up these values a little faster now. And it's going to start to look like something familiar. Okay. So I'm going to close this one. I'm just going to bump up to 10 for a second. Okay. But when we go to 100, we'll really be able to see what's going on. Okay. So as of right now, it looks somewhat uniformly distributed. This doesn't really look like anything right now. right? And I'm referring to the histogram here. Okay, it doesn't really seem to be taking on much of any particular shape. Although I am noticing that it does appear to be centered where the population is centered. Okay. But let's keep going here. Okay. So I'm going to go up to 100, and it might start to become evident now what is going to happen once I try 100. And actually, this was a good 100. Usually, when I hit k equals 100 here for 100 samples, this takes on a particular shape a little more than it is right now. Okay. And this is because, again, this is random, so there's no guarantee that my samples are going to come out the way I expect here. But again, this is what it would look like if I sent out 100 students, each survey 25 people, average the IQ, report that back to me, and then I put it in this histogram. Okay. All right, so let's bump up to 1,000, and then we'll really be able to see what's going on here. So now you can see if I sent out 1,000 students to survey 25 people and average their IQ and report it back to me, this is how those average IQs would be distributed. Okay. At least for one example, this is how they would be distributed. But notice it looks a lot like the normal distribution, right? It looks symmetric, it looks bell shaped, and that's because it is. Okay. I'm going to do something here where it'll make it a little more evident that that is indeed normal. Oh, and I did something that made the computer mad here. Let me fix something. Okay, here we go. And actually, I'm still missing one of the lines I wanted. Let me see here what's going on. Uh, More thing I need to fix. There we go. Here we are. Okay. So now you can see that that histogram does seem to be relatively normal. And so the idea is if we were to continue to take samples of 25, find the average of those samples, and then add them to this histogram, it's going to look more and more and more like that red curve there, that normal distribution. And that normal distribution is our sampling distribution. Okay? It's supposed to essentially be, again, how all samples would be distributed, but specifically samples of size 25 from this population with mean 100 and standard deviation 15. Okay, so this is really neat. If you are sampling from a normal population, the sampling distribution will also be normal. Okay. Which this is really cool because we know how to um, make calculations involving normal distributions using our calculator pretty easily. Okay. So that means we'll be able to do this with sampling distributions as well. All right, so let's go back to our notes here. Okay. So here's actually kind of a picture of what we were just looking at if you want to refer back to it later. Okay. But I'm going to have us move on down here and let's see what we have here. Okay. So this box has a lot of information in it, and I'll try to summarize it in another way, maybe here in a minute. But is what we have is at the very top, they're telling us what the mean and standard deviation would be for a sampling distribution of samples of size n. And so let's go kind of record that over here in a little bit more compact way. Okay. So I'm going to say the mean of a, I'm going to say the mean of the sampling distribution And I'm going to say of X bars to make it clear that the sampling distribution that we're looking at is the distribution of sample means. Okay. So the mean of the sampling distribution of X bars for samples of size n, we're going to write it like this. We're going to write it as sigma. Sorry, not sigma. We're going to write it as mu sub X bar. So this is letting us know that we are finding the population mean of all of the X bars. And it ends up that this is equal to just the mean of the population. Okay, so this right here is a description of this, while a description of this would just be that this is the mean of the population. All right, and to save myself a little writing, I'm going to try to copy this here in a second and replace the word mean with standard deviation so that we can write down the standard deviation formula as well. There we go. Okay. So yeah, this is you know what? I'm going to just scoot that right below it. There we go. So the standard deviation of the sampling distribution of X bars for samples of size n, I know it's a mouthful. This is going to be notated with a sigma and then an X bar as a subscript. Again, to note that this is the standard deviation for all of those sample means. Okay. And it ends up, to find this, you will just take the population standard deviation and divide it by the square root of the sample sizes. Okay. So I do want to, again, arrow to this, saying that this thing right here is that standard deviation of the sampling distribution, while this sigma up here, this is, again, the standard deviation for the population. Okay. And this also explains one thing that you may have noticed here. Actually, both of these explain something that you might have noticed. Okay. So let me actually go back to our picture here that we were looking at. And so the sampling distribution, again, is the curve in red, while the population is the one in green here. And you'll notice, again, they're both centered at 100. Okay? So they both should have the same mean. Okay? Now, is where they differ is the red one, the sampling distribution, is much more narrow. Okay? And you can see this actually in the formula for the standard deviation of the sampling distribution. Okay. And let me go show you what makes this, or the connection here. So if we come back over here, you can see that to get this standard deviation of the sampling distribution, we have to take the standard deviation that we had for the population and then divide it by something. So we're going to be making it smaller. And so that's why your sampling distributions are more compact. Okay. Well, that's one reason. Okay. The other reason they're more compact is that samples themselves are less variable than individual observations. That's the real reason why it's more compact. Okay. So let's come over here and let's see what we have. So this says the World Health Organization reports that the distribution of ages at time of death in the US has a mean of 79.8 years and a standard deviation of 15.5 years based on death certificates. Researchers plan to take a random sample of 100 American death certificates. And so in part A is what we're asked is what are the mean and standard deviation of the sampling distribution of the mean age at death, X bar, for samples of 100 American death certificates. So here's the idea. Okay. We are going to be looking at the sampling distribution for samples of size 100. And our statistic of interest is going to be X bar, the sample means. Okay. So the mean of our sampling distribution of X bars should just be equal to the population mean, which we're told the population mean here is 79.8. Okay. All right. The other thing we were asked for was the standard deviation. So the standard deviation of our sampling distribution is just equal to the population standard deviation over the square root of the sample size. So let's go ahead and write in what the population standard deviation is. It's 15.5. And then we want to divide this by the square root of the sample size. So we're working with samples of size 100. So this is going to come out to actually 1.55 here. So we have found the mean and standard deviation for the sampling distribution of X bars for samples of size 100. All right. And this next example is kind of silly until I actually move us over. But here's the idea. When we are going to be making these sketches, I'll probably sketch the normal distribution almost exactly the same every time because I'm just trying to get a visual of what's going on. Okay. So if I were to say be talking about the population here, the way that I would represent this normal distribution for the population is I would make my normal curve like this, and I'd write an n here, and I'd write in what the mean is, which was 79.8, and the standard deviation was 15.5. There we go. And similarly, if I were to do this for the sampling distribution, and again, I'd write in my mean, which should be the exact same. But then I have 1.55 here for the standard deviation. Okay. So yeah, this is how I'll sketch them in class or in the videos as we're working through these types of questions. But in reality, these two things actually look different. Okay. They're both going to be centered at 79.8, but one of them has a much smaller standard deviation and is therefore going to be much more compact. Okay. And so I want you to see what it actually looks like over here on the right. Okay. So this is those two normal distributions plotted next to each other. And you can see that sampling distribution is just much more compact. Okay. And the idea is with a sample of 100, it's going to be very hard for that average to vary much from the population average. It would have to be a very extreme sample to do so. All right. So this here in the box is something I've actually already mentioned, which is that if you sample from a normal distribution, the sampling distribution will be normal as well. That's what this box is telling us. Okay. And specifically, it is telling us that if this is the normal distribution that we're sampling from, this is what the sampling distribution will look like. Okay. All right. So let's go ahead and give one of these a try. Yeah. So example 2 here says Judy's doctor is concerned that she may have hypokalemia, low potassium in the blood. Judy's measured potassium level varies according to the normal distribution with mean 3.8 and sigma 0.2. Okay. So is what we're kind of saying is we already know actually Judy's mean and standard deviation for her potassium levels, but we're going to observe something here. Okay. And next it says a patient is classified as hypokalemic if their potassium level is less than 3.5 millimoles per liter. And so you can see her mean potassium level, it's only 0.3 higher than what would be classified as hypokalemic. So you could imagine that if she went in on a bad day, she might be classified as hypokalemic, even though she's not. Okay. But in order to try to make sure that this doesn't happen, we're instead going to take 4 samples of Judy's potassium levels. We're going to measure it once every day for 4 days. Okay. And so is what we want to do is try to answer this question here in A, which is what is the probability that Judy's mean potassium level over the 4 days would classify her as hypokalemic? Okay. So we are working with samples of size 4. Okay. I want to emphasize that. Maybe I'll write n equals 4 up here. Okay. And so our normal distribution that we're going to be working with is going to be a sampling distribution, but its mean should be that of the population, which is 3.8. But for our standard deviation, we want to take the population standard deviation and divide it by the square root of the sample size. Okay. So there's our normal distribution. Judy's potassium level would be considered hypokalemic if it were less than 3.5. So that's somewhere over here to the left of 3.8. And so we want to find the probability that if she were to take 4 measurements, that her average would actually be less than or equal to 3.5 millimoles per liter. So we can do this using normal CDF. This is a tool we already know how to use. So you can see over here, there's no lower bound, so I'll use minus E99. The upper bound is that 3.5. My mean is 3.8. And when I say mean, I mean not just the mean of the population, but the mean of my sampling distribution. And then finally, my standard deviation for my sampling distribution. There we go. And so let's go ahead and plug that into our calculators here together. So if I were to hit second vars and then number 2 for normal CDF, then I can start typing some of this in here. And for instance, that 0.2 over the square root of 4, you can type it in just like that. Okay. This is an example where it is actually kind of silly to type it in like this because it simplifies nicely. But a lot of times it doesn't. And so you'll want to type it in like this. That way you don't lose any accuracy by trying to find the decimal approximation. All right. And so I'm getting about 0.001. Got the news popping up here. Let me fix that. There we go. So we have 0.001. So if we take 4 measurements, it's very unlikely that we will accidentally classify Judy as hypokalemic. Yeah. However, let's see what happens if we were to take a single measurement. Okay. And so A and B here, the reason I have these 2 questions right next to each other is that in 1, we need a sampling distribution because we have a sample of size 4. In B, you can see that it says a single potassium measurement. Okay. This means we will not be working with the sampling distribution. We're just going to be working with the population. The population describes how individual observations are distributed. Okay. So when I go to write in which normal distribution I'm working with, it will have the same mean because the population and the sampling distribution have the same mean. But again, I'm working with the population, so I'll just leave that standard deviation as 0.2 there. And then again, I'll shade in very roughly where I think 3.5 would be. And in terms of our calculation, it's going to be just like this one, other than our standard deviation is now no longer 0.2 over 4, it's just 0.2. And so let's go see what this gives us. Here we go. So one quick way of fixing this problem is you could just hit second and then the enter button, and what you typed in previously will pop up. And I just need to delete that divided by the square root of 4. There we go. And so now I'm getting about 0.07. Let's go record that. So this is nearly a 7% chance that we would diagnose her as hypokalemic if we only took one measurement, versus this is less than a 1% chance of us diagnosing her as hypokalemic if we were to average 4 measurements. All right, let's check out part C. So in C here, it says, what is the blood potassium level L such that the probability is only 0.05 that the average of 4 measurements is less than L? So is what they're trying to tell us is that there's some spot here on the x-axis, L, such that the area to the left of it is only 0.05. Okay. Or the probability of landing at L or below is 0.05. Okay. Now, this does say for 4 measurements, so we will be working with our sampling distribution. Oop, that's not what I wanted to write. I want 0.2 over the square root of 4. There we go. All right, so you can see that this is a very different question. In the previous questions, we were asked to find a probability. Here, we're being told that the probability is 0.05. Okay. So we're actually being asked to find something different, not a probability, but some potassium level L. Okay. And we have a tool that's specifically designed for this. That tool is inverse norm. Now remember, with inverse norm, I want to enter the area to the left here first. Okay. Now this is perfect because the area I'm given is the area to the left, so we don't have to do anything tricky here. All right, I'm going to scoot this over a little more. There we go. Now the nice thing about inverse norm is the only other 2 things I have to type in are the mean and the standard deviation, and then we can get this in the calculator. All right, so let's go find this potassium level. So we will hit the same button here at the same 2 buttons at the start here, which is second and vars. But this time we want number 3 for inverse norm. We'll type in that area. We'll type in the mean. And then we'll type in our standard deviation. There we go. And like I've mentioned in the previous video, I'm always going to leave this on left because we don't all have the center and right setting on our calculator. And there we go. We're getting about 3.6. So let's go record that. What is this? Micromoles. I think it was micromoles per liter. Let me go up and look. Yeah, micromoles per liter. Okay. So this right here, the way to interpret what we're seeing here is that 5% of the time, Judy's potassium levels for samples, well, let me restart that because I was going to explain it without samples of 4. We do have samples of size 4 here. So if we were to take samples of size 4 from Judy, okay, there's only a 5% chance that it'll be 3.6 or lower. Okay. That's what this is telling us. Okay. Now, there's something I didn't talk about much as we were doing this because it was right in the box above. But one thing that was really important here was that they told us that the population was normally distributed. That's how we knew that the sampling distribution would also be normally distributed. Okay? Because if that sampling distribution is not normal, we can't use normal CDF or inverse norm to answer questions about the sampling distribution. So this is a really important part of the question, even though I didn't talk about it at first. Okay. Now, the question's going to be next, well, what if the population's not normally distributed? Then what? Okay. And let's go find out. Okay. So, is what we actually have in this, I'll go back up to that box here in a minute. Okay. Is what we have here is we have some population distribution. Here in box A. The rest of these are sampling distributions. All right. And so here's the deal. That population, it's skewed to the right. Okay. But is what I want you to see with these sampling distributions is they are all approximately normal. Okay. But you can see once you get to n equals 30, it looks more normal than at n equals 15. And at n equals 60, it might look more normal than at n equals 30. Okay. And there's a reason for this. As n increases in size, the sampling distributions will become more and more normal. All right. This is called the central limit theorem, actually, which is kind of up here. Okay. But here's how we're going to use this information. Okay. And I still have some more details to add here that I haven't said. Okay. So for one, let's focus in on this bottom half here. Okay. So this says the normal distribution may be used to approximate a sampling distribution of sample means if either of the two things happen. So the second one is the one that we already know. Okay. If the population is normally distributed, the sampling distribution is going to be normal too. Okay. If, though, the population is not normally distributed, we can still assume that the sampling distribution is approximately normal if the sample size n is at least 30. Okay. So if n is greater than or equal to 30, we do not need the population to be normally distributed to guarantee that the sampling distribution is approximately normal. Okay. So every time we need to check that one of these two things is true before we start trying to assume that your sampling distribution is normal. Okay. And so we're going to see that in this last example. So here in example 3, it says a glass tube maker claims that his tubes have a mean length of 9 centimeters with a standard deviation of 0.5 centimeters. What is the probability that a random sample of 40 tubes will have a mean between 8.8 centimeters and 9.2 centimeters? Okay, so let's write up here, first of all, that we are working with a normal distribution that has a mean of 9 centimeters. Now, also, we're working with samples of size 40, and the population standard deviation is 0.5. Okay. But I will admit, I jumped the gun here a little bit. Okay. Um, the fact that I've already written in that this is normal means I have not done the thinking process that I should have done so far. Okay. So notice in this question, it doesn't make any mention that the population is normally distributed. Okay. And it may not be, but it might be, who knows? But it ends up it doesn't matter here because we're going to be working with samples of size 40. Okay. This number here is bigger than or equal to 30. which means that we can guarantee that the sampling distribution will be approximately normal. Okay. So we're in luck. We can do this. Okay. But yeah, we wanted to know what's the probability that a random sample of these 42s will have a mean between 8.8 and 9.2. So let's go ahead and just put on here where we think 8.8 and 9.2 might be. I think just a little bit to the left, a little bit to the right of 9 would be sufficient here. And so the probability, or the shaded area we're looking for, is right here. And so all we need to do now is use our normal CDF. We'll put in our lower bound. We'll put in our upper bound. We'll put in our mean of the sampling distribution and our standard deviation of the sampling distribution for samples of size 40. Let me write that a little bit cleaner. 0.5 over the square root of 40. There we go. All right, and let's go figure out what probability we get. So I'm going to go ahead and I'm going to hit second bars 2, and I'll type in all this information here. There we go. And let's go ahead and hit paste. And so we're getting here about 0.99. So this is very likely to happen. Now, we will be using the skills from this video to do our next two major applications, which will be confidence intervals and hypothesis tests. All right, and that wraps up the distribution of the sample mean.